Hello, everyone. We're going to do a webinar today about how to migrate databases into a Red Hat OpenShift cluster using StorageOS. And we're going to do actually the live migration. We're going to discuss a bit of how we're going to run those databases and an architectural model that is the fact that we're running containers is giving us. So we're going to discuss a few of different models and topologies that we can come up, and we're going to explore that different topology. My name is Ferran. I'm an engineer at StorageOS. With me is also Paul Sobi, my colleague that later on will come into the call as well, or into the webinar. We're going to do some Q&A at the end. What we're going to plan to do today is get a bit into the context of where we are, and we're going to go into live demo, play around a bit with the systems, with an OpenShift cluster, and then we're going to do a Q&A session at the end. You can post all the questions you want in the Q&A section, and my colleagues will handle them and ask later on, and we can have a discussion at the end. To give you a bit of context, we're going to use the OpenShift cluster, and we're going to use the StorageOS. Who we are. We are a company that built a product or built a software, which is StorageOS. StorageOS is a cloud-native software-defined storage for running containerized applications in production. We're agnostic from different platforms, so we're going to do OpenShift today, but we can run it on different orchestrators as well, and it will give us the capacity to do what we need to do in terms of databases in production. One of the models we want to discuss today is database as a service. What does that mean? That can mean different things for different people, according to your background, what you read, or actually how you want to define it. But in the end, what we're trying to do here is define a few goals that we want to achieve and we want our system to give us, so we are not restricted to certain architectures when we are running those databases from a systems point of view, from an architectural point of view. Where this database placed, which hosts are they running, how are they running, if they are tunable, etc. So we're going to look for an environment where we have application-centric storage. What does that mean? It means that we want to avoid having these hardware systems that will present storage to virtual machines or to operative systems, and from there run applications on top that use those file systems. Instead, we're going to say, I have this application, which is a database. This application needs a certain amount of storage, and I want you, storage system, to give me that capacity. This is an important objective because it will allow us to do a lot of fun things that we will see later. Based on that, we're going to run on a declarative and reproducible environment. We're using a Kubernetes-based system, so OpenShift. Most of the things are declarative, and yeah, we're going to use a lot of YAMLs. One of the interesting things about running this database as a service is the fact that we can start tuning databases for the workloads that they are running on. And in the demo, we're going to go a bit into more detail why I mean by this. With that, we can start leveraging also OpenShift and the service and how the DNS works and the networking works to have an abstraction on the endpoints. We don't want to need virtual IPs or floating IPs that move into different instances of a database, etc. So we can leverage the good things that the container orchestrator is giving us. And we want horizontal scalability. Traditional databases, mostly relational databases, require vertical scalability, which means stopping things, making machines bigger, more memory, more CPU, more disk, starting the database, which is not great. If we want to avoid downtime, we move that database workload to a passive server, which means that we are using two big machines, but actually only one is doing actual work. And therefore, we're wasting money, we're wasting capacity, and it's difficult to manage. So what we're trying to achieve here is something that is easy to manage, that it can be reproducible, and it's easy to handle, that is API-based, that the endpoints are handled for us, failovers happen under the hood, and we don't need to know, or we don't need to care, and we can scale easily. So what we're going to do, this is the demo we're going to do, and I'm just going to give you a bit of context of what we are trying to achieve. We're going to have a Postgres database. on a random server, VM. Of course, on production, you would have a big server that you have a lot of databases in it. Let's, for instance, think about Amazon Web Services RDS. We have this big instance which has a big chunk of memory, one big computer, disk capacity, CPU, etc. We put all our databases there, and we can access through DNS. Whether you manage these or use a managed service, the principle is the same. You might need 2 different computers in 2 different places with the same amount of resources to be able to run once. So, for instance, high availability. We can have read replicas as well, for instance, for this case with Postgres. But in the end, we need a layer somewhere to manage these automatic failovers and to manage moving IPs or changing DNSs, etc. So instead of doing that, we're going to explore a different model of running these databases. We're going to have an OpenShift cluster with a few nodes, a few workers. We're going to install, or actually, we have installed StorageOS on those workers. StorageOS runs as a container on them, and will aggregate the capacity of those nodes to provision disk capacity towards applications. In this case, stateful applications, in this case, a Postgres. So what we're going to do is we're going to deploy Postgres in OpenShift. And instead of having a one-to-one map, we're going to create a different project in OpenShift. So if you're familiar with Kubernetes, a Kubernetes namespace. And for every database we have in this big Postgres instance, we're going to have one different instance of Postgres for that database. And later on, we're going to explore again why this. And of course, this will have caveats and this will have benefits. I think it's interesting to just take an approach of see what are my needs and what are the caveats do I have on this model versus the other model. While using one big server can be problematic because of scalability, because of manageability, etc., having many can have an overflow or an overhead of running database instances. So we're going to discuss a bit of the pros and cons, and we're going to try to do that from a flexible point of view. So let's go and let's do a live demo here. What do I have? What do I have is an OpenShift cluster that has 3 masters and 3 workers running on AWS. There's few VMs. It's a fairly small cluster to be an OpenShift cluster. Usually you have a Red Hat OpenShift container platform can host a lot of worker nodes. In this case, I only need this for the time being, just for the demo. Now, I'm going to go to the command line and let's check. We see these nodes again, few workers, few masters, 3 and 3. And as I mentioned before, StorageOS is installed. StorageOS installs the main component, which is the daemon set. Make this a bit smaller so we can all read this. Has 3 daemon sets, so meaning one instance of this pod on every node, and we will aggregate this capacity in one cluster. When this is running, and just for context, StorageOS has a UI access through the API port. So I'm going to use the StorageOS user interface here to keep you showing things. Obviously, we have a CLI and things like that, but for the demo, it's going to be a bit easier to see what we're doing. Cool. By the way, remember that you can keep asking questions on the Q&A while I'm doing things here. So just keep shooting and keep firing questions at any point in time. Cool. Let's have a look. We have StorageOS installed. We have OpenShift, an OpenShift cluster. Now, let's go have a look at the Postgres machine. Again, another VM in Amazon that we are running Postgres in there. For instance, let's have a look. So we can see we're just running a standard Postgres. It's a 7.12. There's a newer version already, but it's a standard database. What do we have in it? We have one database for every application. Obviously, you could have different databases for whether you have a business case or microservice or different areas of your application. Here, I did this dummy names so we can see easily and we can correlate those applications and those databases to specific instances of Postgres. I just inserted a bit of random data with pgbench into those databases. So just to give you a bit of context, they are not empty databases. Have a table, standard pgbench. If you're not familiar with the tool, it's just a benchmarking tool for Postgres. And we just have data here. Of course, it's small, but there are many more. So just random data that we can use. Cool. So this server, I'm going to show you the IP because it's important. Or you could use DNS or IP base. I'm going to use IP for simplicity here today. But we're going to reference this Postgres. We're going to connect from OpenShift, and we're going to migrate the data from here to the new place. So this. We're going to use this IP address. It's a private IP address that I have in the subnet. So I need connectivity between the OpenShift cluster and this machine. No big deal, but for context. Cool. Let's start. By the way, everything I'm doing here is available in GitHub. So you can use these. It's just an example. I'm going to do a lot of operations by hand that I would highly recommend that you do in a CI/CD environment. So I'm going to do it in a way that you can see what we're doing and you can see the operations that are happening. But obviously, this is something you want to do from a pipeline, or whether it's Jenkins or Travis CI. So let's have a look. I have a namespace for a project in OpenShift for every application that we want to create. And we're going to use this microservice architecture. Again, this is one way of doing it. You can split your namespaces in the way that feels better to you or is better for your use case. I'm just going to use different applications, different projects, and I'm going to install one Postgres application in every single one of them. So to do that, really fast, really tiny, I have a tiny file with the name of the databases that we're going to use. I'm just going to iterate to it and create the databases. What am I going to use to create this database in OpenShift? We're going to use stateful sets. Stateful set, if you're not familiar with it, is a Kubernetes controller that will help us to run stateful applications. It will, similarly to a deployment, if you're more familiar with it, but it has some specific requirements that enforces to guarantee that our data has consistency and follows a different workflow or life cycle than a deployment. We're using a fairly standard Postgres image. Probably some of you have seen that there are operators for Postgres, and those are great. They simplify some of your operations. But I'm trying to do something here in the low level so you can see what we're doing without that many layers of abstraction. And the same thing that we're doing today could apply for a MariaDB or even Elasticsearch or other tools. Where are we mounting the data? How are we using persistent volume claims to back up the data of those containers? We're using a volume to mount into PG data. If you want to use the transactional partition in a different place, you can do it here. And we will tell Kubernetes in our volume claim template where or how to provision the capacity, the volume. Once again, this is application-centric. We're saying we want a database and we want some sort of storage, in this case, read-write once, block-based device, low latency and fast performance, that is defined according to this declarative YAML. So we're going to ask for 10 gigabytes, and we're going to use the storage class that references StorageOS. So let's do this. So I'm just going to iterate over the applications, and for every single namespace of it, I'm going to create the YAMLs for this specific for this specific directory. So let's have a look so you can read a bit better. it's very, very simple. I'm just doing an OC create of the YAMLs that I have in this directory for every namespace that I have. Okay, fairly simple. Let's have a look in the Openshift UI, which is actually great for this kind of operations, workloads, pods, projects. So we can see that the Postgres applications are already starting. Some of them are already started. And because this is declarative, and again, we want something that is automatable, the names are the same. Kubernetes service model, the Kubernetes service model in the networking is abstracting us to have to care about how these things are provisioned and how these things are accessible. So we have a pod name, Postgres 0, on this app for namespace, and we have one for every single one of the ones I created. And they're just starting. And for every single one of them, for every single namespace, we have a different persistent volume claim. So let's have a look. System volume claims. So once again, namespace, the PVC name, they are called the same, but they are segmented through OpenShift namespacing or OpenShift projects. Again, 10 gigabytes for each, and we are just starting different instances of Postgres on different applications, and they're going to be segmented one to each other. There are different containers, different pods. Even in OpenShift, because it uses Open vSwitch on the networking, you can start restricting network access in between namespaces if that's something you really need. So when we go to the StorageOS user interface, what we can see is StorageOS automatically maps out the persistent volume claim namespaces that we have provisioned. And all of this is dynamically provisioned. So I just declared a few resources and a few YAMLs. And with the tiny loop, we have databases and namespaces and volumes and pods just starting right away. So for instance, if we go to one of them, we can see the StorageOS volume on that specific namespace. In this case, I enable replication by default, meaning one replica for this volume. For StorageOS, this means 2 instances of the data that are always in sync. So StorageOS uses synchronous replication. So every time we write to the primary volume, it also writes to a replica before it acknowledges that write to the file system that is mounting the Postgres database. In this specific case, let's make this a bit bigger, the application is attached on the node 216. Maybe you can see that here. And is actually the same node where the master is located. So input-output operations are going to go from the application that is running in this node towards StorageOS that is storing the data in the same node. And it's also sending that data to a different place. So it's sending the data to a different node. We're going to have low latency. We can also have volumes that are not starting on, that don't have the data on the same place as the application. So I'm just going to try to find one of them for you. By default, StorageOS tries to place or tries to influence volumes to be in the same place as the applications, but it doesn't have to. So you can see here that the attachments and the master node are in the same node. That is because the StorageOS scheduler is telling Kubernetes, if you can, put the application close to the data, so 80 and 80. So you can see that one by one is allocating the data where we write and we read from to the same place where the database is executing is located. Doesn't have to. We can start that database anywhere in the cluster. The data without moving will be accessible. And that's where we leverage the storage system here. Let's keep going onto the migration then. Yeah, the database is run. Let's see, just for people that like CLI. Now, bottom PVC that is serving on this specific project. We need to connect now Kubernetes or the OpenShift cluster itself with that Postgres instance that I showed you before, so where we had the actual data. How do we do that? We do that using an external service. An external service is a way to define a DNS name and a few endpoints that are hard-coded to specific IP, rather than letting Kubernetes decide which are the endpoints that we're going to use for the service. So let's have a look here, external service. So we're going to have a service called PG in a specific namespace that we're going to reference later on. And this service will map out to an endpoint that has hard-coded the address where it's coming from. You can put multiple addresses here, and it will do a round robin to access. So I'm going to create this, and from inside my OpenShift cluster, I will just reference this service to access the production database. Now, let's go and start importing data. Once again, I'm going to repeat this again. Do this on a CI/CD environment. Don't do this by hand. I'm just showing you what are we doing and how to do it. We're going to create a job for every database that we want to migrate. A job is a controller that will start an instance of a pod, and it will run it, in this case, once. And this job will do one thing and one thing only. In this particular case, it's going to create database in the local Postgres instance, database that we are serving from an environmental variable, and it will run a PG dump, so a dump from the database, piping towards a PG restore. You can probably already see that the PG dump is coming from the production cluster, and the PG restore is towards the database that I have in that specific namespace inside OpenShift. Of course, if you have big databases, you're not going to do this. You're going to do probably an intermediate solution where you can take backups that you already have and port them using a job to the OpenShift instances. I'm doing this for the sake of the demo, but obviously there are different approaches here. As you can see, most of the variables that I have here, database, the user, the source, are coming from an environmental variable. And that's coming from a config map. Let's have a look at that config map. User and password, that's obviously something that you will use from your CI/CD. You will use secrets and do it properly. This is just for simplicity. Interesting bit is the source. Remember, we just created that external service that is pointing to the production cluster, because I'm using the Kubernetes services and OpenShift and I'm using OpenShift and Kubernetes wording one to the other, but I guess you get the point. So we can use those services to leverage the capacity that all of them are called the same. So when we want to access those databases, we're accessing service name.namespace, and we will be able to access that external database that we just hard-coded the IP. Then we will say the destination, because this job will create a pod on every namespace that we created our microservice or our applications. All of them are called the same. Pod name, .service name, it's enough inside the namespace. You might say, okay, but what about the DB? Database is something we're going to patch on the fly. And if you have different databases names, you can use template tools here, like Customize or Helm or anything that suits you. So here, I'm just going to do a tiny simple patch. So let's create the config map first. Same as I did before, just a while loop that goes through all the applications and creates for every application that config map. Now, let's have a look at the patch. It's a simple patch that will change the environmental variable from DB to the application that we have. So now, instead of having the database as an environmental variable, we have every single one of them. Let's take one of them, doesn't matter much. So for instance, for app 7, we can see the database is app 7 already. So now we have one config map that references to the right database on its own namespace or in its own project. So the only thing I have to do now, similar as before, is run that job, that created job that will create one pod on every namespace, and it will throw the migration for us. Once again, I'm just doing the same thing, just iterating over them and creating the job. Let's have a look at the applications. So we have one of these job applications for every namespace. Once again, port here. And every single one of them is completed because there is not much data. But if it takes longer, it takes longer. It's quite asynchronous. It goes one by one, and it creates that that database. If we look at the logs of the pod that job created, we just see pg restore output, just standard output. If there was a failure on the network or something, we could see it here. Again, we can leverage the orchestrator to do the job for us in a very automated and in a very simple way, and even do that on a fairly self-contained way. If one of them fails, the other one maybe might be able to keep running. So we have disaggregated concerns here, and we are not having trouble if we don't have to handle errors and issues that one will affect the other. You can use the same model that I used also for migrating backups from production to developer clusters, where you might want this kind of model where different teams have access to different areas of the data. Let's go have a look actually into one of these spots. Let's go to the terminal. Let's say, for instance, one of them, it doesn't matter which one, I'm going to go to this spot and get a terminal into it. Ooh, this. If I do the F, one thing we can see, fun, is that we can see in PG data the StorageOS volume that is mounted. That is what is keeping us safe. So that's what's keeping this data safe from node restarts, from node failures, and from other issues that can happen in the cluster. So now let's go have a look at the data. We can see that in app3, we have the database, app3, not any other, just that one. Let's have a look at the table. And once again, we just have the data that we saw before. Sorry. Just data as random numbers. Cool. We just migrated in a tiny few minutes. We came from one database, one instance of a database that is kind of difficult to manage, towards, with a few YAMLs and 10 minutes of work, a system that can run many databases on a containerized solution. Now, you might say, okay, this is fine, but what about the safety guards that I'm putting for my HA Postgres instances? Let's go and play around with this a bit. So, for instance, we have this in app 8 that is running on a specific node, node 80, and we're going to move that application on a different node. So let's go to app 80, app 8, pod. Let's go a bit backwards. We have more space. We can see that the node that is running is the one I mentioned before. Okay, I just cordoned this node. So what I'm doing here is avoiding for this application to be able to start on this node again. So this node will not host any more scheduling. It will not schedule any more pods during the time that is cordoned. So I'm just going to go and delete the pod. Postgres 0. And immediately it's starting on a different node. So we will see that right away it will start and it will mount the volume that it was using before. So the data is going to be the same. See, okay, it's ready. So let's get into it. Same as before, if I do a df, we can see that in PG data, it's served by StorageOS volume. And here, I can access the data as I did before. So here we have app 8, no problem. So now we just started our application on a complete different node, and the data is just available. Obviously, before it was doing reads from the local, and now is going through the network. StorageOS is handling that under the hood, under the file system that is using that Postgres. So there is a bit of latency in the input-output operations, but we have the flexibility. We can start applications wherever. Second thing that we want to check. What happens if the node where the master goes down? Keep in mind, this is the node 180. And let's go have a look. I have, for instance, access to the SSH of the nodes that are using the workers. So here, node 80, you can see, host name, once again, 180. I'm just gonna stop that node. You can crash hard if you want. These volumes are replicated. So we are triggering actually a failure. StorageOS automatically has promoted really fast, in a matter of milliseconds, where the replica was located. The replica has been promoted now to become the primary under the hood, and a new replica has been provisioned automatically. Remember, this is declarative. We want to move away from having to do changes. The system is told that it has to have one instance or one replica, so 2 instances of data. If I go check the node, I can see that the node is offline. StorageOS has its own health checks, and it has the master in this specific node. Now, how does that look like for the application? Same application as before. We have access to data. Nothing happened to that specific application. We can access the data as we did before. We have access to the file system, even though where this application was writing as a node failed. So we just have, leveraging the StorageOS component here, a capacity to fail over volumes and a capacity to fail automatically self-heal in case of failure, which, to be honest, I feel this is, as an operator myself, this is really great. I rebooted the node, it just came back, health check. Okay, now it's available to have capacity provision there once again. Recap a bit. Let's see, once again, what were the goals that we had originally. Application-centric, we just saw that. We just said, I want 10 applications that use capacity, and I want 10 gigs for each of one. And by the way, it needs to be replicated. Check. Declarative and reproducible, we're using standard YAMLs from OpenShift, and it's quite trivial to see that that's declarative. Workload-specific database tuning. That is one thing that we didn't do, but I think is where this topology opens a lot of doors. When we have one instance of Postgres that is really big and really bulky, and we have different sorts of applications running their databases there, it means that we have different I/O workloads or profiles of access to data that might be conflicting one to the other. For instance, we can have app 1 being an access to a newspaper or a magazine that have a lot of reads. Doesn't have many writes. So we want to do a lot of certain kind of caching and a lot of access through fast retrieval of some articles, while other applications are maybe designed to do more events or a lot of small writes. So when we're tuning our database, we cannot decide what to tune for. Do we tune for a lot of reads, for a lot of small writes, for big writes, for a stream of constant data, for a lot of transactions per second? Bandwidth, it's difficult to say, I'm going to do really fast and I'm going to do everything really well. It's impossible. So by splitting the problem in different areas, we are capable to tune specifically every instance for what's needed. App 1 has a lot of read requirements. Let's tune it for it. App 3, in this case, let's say App 3 is a transactional-based system that we need to add a lot of small grids and a lot of throughput. Hey, let's tune it for a lot of small grids. We can do that because now we are not constricted to a model that is telling us run something on a big node. And by the way, we have a copy of this that you cannot use because it's only for passive mode. We are also leveraging the capacity that the orchestrator gives us to spin up applications fast, to have life cycles of applications that need to spin up applications fast while they are safe. Obviously, there are caveats. And there is here where we can analyze what is best for me or what is best for you or your team. We showed the database endpoint abstraction by using the same name on every config map. So we connected our jobs from one database towards that new place, leveraging the service model that Kubernetes gives us. We don't have to worry. It all has the same name. We are not making mistakes as humans because the machine has the same name. It's difficult to make those mistakes. I will not end up with application 2 running on the namespace or running on the project for a different team, for a different application, for a different model. So in the end, we avoid issues that we can cause as humans while typing or based on attention. And finally, we just saw that scaling horizontally was fairly easy. We have OpenShift nodes. We have workers, spinning up new workers because StorageOS starts as a daemon set. We'll start in all those nodes. We can provision capacity there. We can spin up more applications, more stateful applications, in this case, Postgres. We can leverage the orchestrator to do that work for us. You can be thinking maybe about replicas for the specific of Postgres, but keep in mind that we're talking about databases. And I just show you a transactional database example. But we can leverage the capacity for containers to spin up fast while keeping the storage safe and fast, low latency and high throughput. We covered a few of these topics, but what does it mean to run stateful applications in a Kubernetes environment? In the end, we are making a difference between stateful applications versus stateless applications. In the end, some applications that require to keep their state locally and some applications that usually delegate their state somewhere else. Stateless application, for instance, a web server, usually ends up being horizontally scalable, but ends up having to delegate the state to a third-party application. For instance, a key value store for sessions. For instance, object store for assets or CSSs and JavaScripts and things like that. Or an Elasticsearch for indexing. So in the end, stateless applications are good because they delegate the state. But what about those applications that hold that state? What about the Postgres? What about the MariaDB or the MySQL? What about Elasticsearch? What about Kafka? We want to leverage that capacity of the orchestrator to spin up those applications fast, to be portable, and to handle all these life cycles that as operational engineers we like, while not keeping into the tides of containers being ephemeral. We are treating these containers as ephemeral while the data is safe, but the containers can be ephemeral. They are actually. We are treating nodes also as ephemeral. In OpenShift, you can lose nodes really easily, or you can just recycle nodes here and there. So you have to be able to have replication and not be tied from pods to be running on a specific node. So if I have 50 nodes in my cluster and I lose 2 of them, it should be fine. I shouldn't be tied to those nodes to hold data there. We obviously need a system that is performant and has flexibility, low latency. Again, these are stateful applications. It needs fast throughput. And once again, the fact that we are application-centric, we are provisioning capacity from an API point of view. So in the end, how are we solving this? Multiple copies of data for automatic failover, synchronous replication, Yes, we have a caveat if we add replication on performance, because we are writing to two different places at the same time, but we are safe. We have to be able to access data from anywhere. We actually show that. You spin up your application anywhere, and it has access to data. And obviously, it has to have low latency and high throughput. These are databases. These are data stores. We need to be able to retrieve that data fast. So demo is kind of finished here, and the things that we want to explore are we covered already. Before I finish, I like to mention a few things. Very often, we come with the performance benchmarking and talks with customers and people in the industry about performance. Actually, we didn't release an independent analyst just released this document where explains and compares different storage solutions in the realm of containers and shows a bit of performance. In actually really good report to have a read. We're going to give you these slides. So this URL is something you're going to be able to access. It's actually a great report. You will see the performance. I can tell you a bit of it about it. I guess you can go and read it. It's actually a great read. It's great to read. You will see that after 2 years, StorageOS making a big effort on performance, it actually pays off a lot. The performance that you get on the systems that I show you are frankly very good. We have a free developer version that is always going to be free. It's a 5 terabyte available for provisioning of persistent volume claims. You have full functionality, but regram many volumes. It's free. You can just register. And on your cluster, as soon as you spin up your cluster, you can just input that license or your account, and it automatically licenses your cluster. We have a platform overview as well, a different URL that will explain a bit of production best practices and a few lessons that we have learned. Documentation, obviously, that's always a good resource. And if you want to speak to me or to any of my team or any of our engineers, we're really, really active on Slack. We're always there, and at least in working hours. And please come engage if you want to install, if you want to talk about licensing, if you want to talk about installation procedures or where are the resources that you're looking for. We are really active there. Cool. So we can pass to questions. I think Paul is gonna come up now. Hope you enjoyed and it's useful from a technical point of view. To be honest, that's my most intention. So let's go into questions, whether they are about StorageOS, the model of databases that we explained, the product, any kind of questions that you're interested in. We're going to try to do our best to answer.
Thank you for a great presentation, Ferran. We do have some questions. Yes. Question from Edward. You mentioned that StorageOS has built-in synchronous replication. Lots of databases, such as Postgres, also have their own built-in replication. So should I use StorageOS or Postgres or both?
That's actually a really good question. Postgres has read replicas. Again, these are for reads. You can have throughput, performance, horizontal scalability. You can increase the capacity to have more reads. StorageOS volume doesn't give you that. What happens if you lose one of these read replicas? You have to have a replica from scratch. What happens if you lose the master? The master usually will have to switch to a read replica. Most of the applications have asynchronous replication, because for writes, usually being eventually consistent is fine. You cannot guarantee that data is going to be saved there. However, there are solutions for active-passive replication for a transactional database or for Postgres itself, which probably can do and does very well. So in the end, it's about flexibility. You can play read replicas while maybe the master holds a StorageOS replica as well. You can hold maybe StorageOS replicas also for the read replicas. Why? Provisioning time. If one of your nodes goes down, do you have to rebuild the whole replica from scratch? Or you already have another copy that you've been syncing over time? In the end, it's flexibility. In the end, it depends on your use case and what you need. For instance, one example I can give you that is a real use case is we have some people running Elasticsearch. They have around 6 terabytes of an index. They have a lot of shards. and they had this in I think 5 to 6 nodes. What happens when they lose one of the nodes? They have to rebuild 1 to 2 terabytes of resharding data. If you have those instances replicated, that data is already there. It can spin up, and StorageOS will do the syncing under the hood. You don't have to move all the data around while you're spinning up the replica already. So once again, it depends on your use case. It's not good or bad to use one or the other. It depends on your use case, and I would suggest to assess based on what you think best.
As with so many things in engineering, the best answer is it depends.
Yeah.
Thank you. We have a question from Anson. The PVCs that were provisioned as part of the demo were 10 gig each. Does that translate to 10 gig consumed backend storage per database?
Mm-hmm. No. StorageOS provisions volumes using a technique called thin provisioning, which means that only the actual data that is written to that file system is stored to disk. So I can provision a 300 gig volume, and if I'm using 300 megabytes is what I will see in the underlying file system that StorageOS is using to store data.
Brilliant, thank you. We have a question from Farzana. Could you recommend some techniques for backing up these databases?
One of the things we have actually in that repository is a backup example. I didn't show because I didn't think it was needed, but you can do jobs, as I did before today for the PG dump. You can do a job to generate backups and store that in different volumes or a third-party object store like S3 in Amazon, things like that. I would recommend that for stateful applications, you use the tools that are designed for that application. It's very common to use snapshots. And actually, at StorageOS, we're implementing snapshots. But it's important to understand what snapshots are and what they are not. Snapshots are a good copy in time of the binary data, but they are not necessarily a backup. So I could use pgdump if you have MySQL extra DB backup, if you don't want blocking operations, or the MySQL dump if you can live with having blocked writes, Elasticsearch snapshots, etc., etc. Why? Imagine a distributed application like Elasticsearch or like Cassandra. Having snapshots of different instances of the data doesn't make a lot of sense. You need the tool to make sense of how the data is distributed and stored. So I would recommend always to use tools specific for that stateful application, that data store.
Brilliant. Thank you very much. And with that, I think, guys, we're just about out of time. So thank you very much for your questions. The ones that we've not got to yet, we've taken notes and we will be getting in touch with you offline. Thank you very much. And thank you, Ferran.
Goodbye.